Hey everybody, welcome to the third video of our calculus series where we will be covering both AB and BC only topics. Today we will be discussing one-sided limits in calculus. So the definition of a one-sided limit is the value that a function approaches as we get closer and closer to a specific x value from only one side. So let's kind of discuss the purpose of these one-sided limits. They become very helpful when we think about what we talked about in our last video, which are the limits that don't exist. And as we discussed, certain limits do not exist because the function does not approach the same value from either side, similar to what you might see in this graph right here. And this is where we can use one-sided limits to evaluate what the function is approaching on one side, so either from the left or the right of that defined x value that we're trying to approach. This helps us still understand the behavior of a function. So let's first take a look at what just the regular or normal limit type question would be, which would be the limit as x approaches a for this function f of x right here. Now again, when we draw a limit, we're just approaching from the left and the right side and seeing what the function is approaching. So from the left side, we're getting closer and closer to a. From the right side, we're getting closer and closer to a. And it's pretty clear that the function is not approaching the same values on the right and the left side of where x equals a. So that means that the limit as x approaches a for this function f of x doesn't exist. So just write DNE, and that's our abbreviation for does not exist. But now if we take a look at our one-sided limits, we'll see that one-sided limits look very, very familiar to what just the normal limit question might look like, but they have one key difference, and that's the minus or plus sign that you'll see after that defined x value that we're approaching. So the minus sign indicates that you want to evaluate the limit by approaching from the left or from below that x equals a value. So right here we have the limit as x approaches a from the left, as we have that minus sign for this function f of x. Nothing really changes in how we try to solve this question, except for the fact that we're only going to approach from the left side. So if we take a look and we're approaching from the left side of x equals a, we see that the function is approaching b. So that's our answer for this one-sided limit. But now, if we take a look at our next one, the limit as x approaches a from the right side, which is what that plus sign indicates, is that you're going to evaluate the limit by approaching the value from the right or from above. So in this case, nothing really changes, except now we're just only evaluating from the right side. So if we approach from the right side of x equals a, we see that the limit will be c. So now that we've defined a one-sided limit, explored its uses, let's take a look at some practice problems. So you might have seen a very similar function to this one, which is known as a step function. And we're going to start by evaluating what the normal limit for this function would be. So we'll start with the limit as x approaches 1 for this step function. Now whenever we have a graph, let's use it to our advantage. And to evaluate a limit, we'll look what the function is approaching from both sides of that defined x value that we're approaching. So from the left, or from the values where x is less than 1, we'll see that the function is approaching 0. Now, if we take a look from the right, or where the values are greater than x equals 1, approaching from that side, we'll see we're getting closer to that value of 1 for the step function. So now we have that problem where the values do not match up as we approach from both sides. And again, this means that the limit does not exist. So write in that DNE. And now we'll try to evaluate the one-sided limits from either side of where x equals 1. So to start, we have the limit as x approaches 1 from the left side, as indicated by that minus right here, for this step function. Again, nothing really changes about our approach for this limit question, only that we will check what the function is approaching from one side, in this case, the left side. And as we see, as we approach from the left side, we're going to that value of 0. And now we'll try to evaluate the limit from the other side. So we have the limit as x approaches 1 from the right, as indicated by this plus, for the step function. Again, nothing's changing, but we're looking from the right side in this sense. If you take a look from the right side, approaching the value of 1. And there we have it. Now let's take a look at another example, kind of like this, except now instead of having the graph, we have the piecewise function defined for h of x. So the first limit we will evaluate is the limit as x approaches 3 from the left. Again, you can tell this by the minus for this function h of x. To evaluate this limit using only a piecewise function, we want to choose the expression that determines the behavior of the function for the values where x is less than 3, since that kind of simulates approaching the limit from the left side. So the expression representing this is 7x minus 3. As we can see, that's where h of x is defined for the values where x is less than or equal to 3. So now we're just going to directly substitute 3 in for x. We'll get 7 times 3 minus 3. So this is just going to be 21 minus 3, which is equal to 18. So our limit as x approaches 3 from the left side of h of x is going to be 18. Now, let's analyze the limit as x approaches 3 from the right side, as we can tell by this plus sign, for this function h of x. To evaluate this limit from the right side, we want to choose the expression that defines the function's behavior for all values where x is greater than 3, as that's going to represent approaching the function's values from the right side. So in this case, that expression is going to be 7x minus 12, x squared minus 12. As we can tell, that's where h of x is defined for the values where x is greater than 3. Now, again, we're just going to directly substitute 3 in for x, and we're going to have 3 squared minus 12. It's going to be 9 minus 12, which is equal to negative 3. So the limit as x approaches 3 from the right side for h of x is going to equal negative 3. Okay. Now you can evaluate one-sided limits for functions with discontinuities given just a graph or even just given the function. But now another case you might see one-sided limits being used is with endpoints of a function. For example, a question similar to this, which is like a half circle equation, and we have both the graph and just the function. I just gave it just to show you guys what it looks like, but we're just going to use the graph for this question. And this is a case where that normal limit for the endpoint, which is at x equals 5, wouldn't exist. So let's start by analyzing the limit as x approaches 5 from the left side. Again, using our graph, we can see that as we approach x equals 5 from the left side of that, our function is approaching 0. Simple, kind of like what we're used to. But if we were to analyze the limit as x approaches 5 from the right, again, seeing that plus sign, for this function g of x, we would run into a slight issue because as you can see, you can't really approach from anywhere greater or the right of x equals 5 because the function isn't defined for the values where x is greater than 5, since x equals 5 is the endpoint of this function. This means that we can't approach from the right side of x equals 5, and if we can't approach from the right side, we can't evaluate that one-sided limit. And we would say that the limit in this case does not exist. So I really hope this video was helpful for you guys. Please comment down any questions or video requests you have, and make sure to subscribe to keep up with the rest of the calculus series and our other STEM content.